First, let's derive the locus S. We'll start with two arbitrary points on the parabola e squared equals x. Let's call them P and Q. Their coordinates can be written in terms of y. P is at y1 squared y1, and Q is at y2 squared y2. We need the area of the region enclosed between the chord PQ and the parabola. The area is 1/6 times the absolute value of y1 minus y2 cubed. This is a known formula for the area between a parabola and a chord. The problem states this area is 4/3. So we set 1/6 times the absolute value of y1 minus y2 cubed equal to 4/3. That means the result is y1 minus y2 equals 2. Let's proceed with that. So a chord on the parabola e squared equals x will enclose an area of 4/3 if and only if its endpoints have y coordinates that differ by 2. This condition is key to finding our locus S. Now that we have the condition y1 minus y2 equals 2, let's find the locus of the midpoint x of the chord PQ. Let the coordinates of the midpoint x be alpha and beta. The midpoint formula gives us alpha equals x1 plus x2 over 2, and beta equals y1 plus y2 over 2. We also know that our points P and Q lie on the parabola e squared equals x. This means x1 is equal to y1 squared, and x2 is equal to y2 squared. Substituting these into the alpha equation, we get alpha equals the sum of the y coordinates squared, all over 2. And the beta equation remains the same. Now we'll use our condition y1 minus y2 equals 2. Let's substitute y1 equals y2 plus 2. Plugging this into the alpha equation, we get alpha equals 1/2 times the quantity y2 plus 2 squared plus y2 squared. And for beta, we get beta equals 1/2 times y2 plus 2 plus y2. This simplifies to beta equals y2 plus 1. From this beta equation, we can express y2 in terms of beta. y2 equals beta minus 1. Now we can substitute this into the alpha equation. Alpha equals 1/2 times beta minus 1 plus 2 squared plus beta minus 1 squared. This simplifies to alpha equals 1/2 times the quantity beta plus 1 squared plus beta minus 1 squared. This is a standard algebraic expansion that simplifies beautifully. The cross terms plus 2 beta and minus 2 beta cancel out. We are left with alpha equals 1/2 times 2 beta squared plus 2, which simplifies to beta squared plus 1. So, the coordinates of the midpoint x satisfy the equation alpha equals beta squared plus 1. This means the locus S of the midpoints is the parabola x equals y squared plus 1. Now that we've found the equation for S, x equals y squared plus 1, we can visualize the region R. Let's review its boundaries. The original parabola e squared equals x. Our new locus S, x equals y squared plus 1, and the vertical lines x equals 1 and x equals 4, all in the first quadrant. Here we see the two parabolas on a coordinate plane. The blue one is y squared equals x. The green one is S, which is x equals y squared plus 1. Notice it's just the original parabola shifted 1 unit to the right. Now, let's add the vertical lines x equals 1 and x equals 4. The shaded area between them and the two curves represents our region R. We need to calculate the area of this shaded region R. The most straightforward way is to integrate with respect to x, from x equals 1 to x equals 4. To do this, we need the equations for the curves in the form y equals f of x. For the first quadrant, where y is non-negative, the original parabola is y equals the square root of x. The original parabola is y equals the square root of x. The locus S, x equals y squared plus 1, becomes y equals the square root of x minus 1. Now, which curve is on top and which is on the bottom for our region R? For any x between 1 and 4, the square root of x will be greater than the square root of x minus 1. This makes sense geometrically as well. The parabola y equals the square root of x is above the parabola y equals the square root of x minus 1 in this region. Therefore, the area of R is the definite integral from 1 to 4 of the difference between the upper curve and the lower curve. That's the integral of the square root of x minus the square root of x minus 1 from 1 to 4. Now, let's evaluate this integral to find the area of R. The integral is the integral of x to the 1/2 power minus x minus 1 to the 1/2 power, all from 1 to 4. We can separate this into two integrals. That gives us the integral of x to the 1/2 dx minus the integral of x minus 1 to the 1/2 dx. Let's solve the first integral. The power rule of integration tells us to add 1 to the power and divide by the new power. So the integral of x to the 1/2 is x to the 3/2 divided by 3/2. Evaluating this from 1 to 4 gives us 14 over 3. Now for the second integral. The antiderivative of x minus 1 to the 1/2 power is similar. It's 2/3 times x minus 1 to the 3/2. The integral of x minus 1 to the 1/2 is 2/3 times x minus 1 to the 3/2. A subtle point here is the lower limit of integration. When x is 1, the term x minus 1 becomes 0. So when we evaluate at x equals 1, we get 0. This changes the lower limit for the integration variable if we were to do a substitution, as noted in the original notes. For now, let's evaluate the antiderivative directly at the original limits. Evaluating the second integral from 1 to 4 gives us 2/3 times the quantity 3 to the 3/2, which simplifies to 2 times the square root of 3. Finally, we subtract the result of the second integral from the first. Area equals 14 over 3 minus 2 times the square root of 3.